Formal talk. Okay, I'm actually, this is slightly experimental. I understand that many of you are high school students slash undergrads slash our own undergrads as well. So I'll be actually talking about my research itself. Okay, I'm not picking a topic that is basic physics or anything, but we'll go through it slowly. I'll try to introduce to you what the current problems are, how we try to make sense of images like this, and you can stop me at any time. Okay, I don't have too much material, so you can stop me at any time. We can go through it. I can go to the board, draw some things. Okay, the point is to it doesn't matter if we don't get to the end. Okay, just stop me at any point. Okay, so most of you may have seen this image. This is the first ever image taken of a black hole. Okay, this is the black hole M87 star, and I'll tell you what this, where this black hole is, what it's doing, etc., as we go along the topic. Okay? So this image, this light that we see, is actually radial light. Okay? So that's the title of my talk. It looks quite different from this snip, okay, of a black hole, which I'm sure all of you have seen from the movie Interstellar. Okay, the black hole in this movie looks much sharper. When you zoom out, you can see this edge is quite sharp, etc. Right? And the reason we don't see we don't make images of that high resolution is just because we're too far away and we don't have the resolution from the Earth. We don't have the resolving power from the Earth. So what should actually look something like that ends up looking like this from our Earth. Okay. But in this talk, I'll try to convince you that this is actually an image of a black hole that is out there in our universe, and this is the first ever such image that we've been able to make. So what you're seeing here, this dark region, is actually the event horizon of an actual black hole out there in the sky. Okay? So I'll try to convince you that that's the case and how this image is constructed, both from the observation side and a little bit from the theory side. Okay, so let's get into it. So this is a supermassive black hole M87 star. It's in the galaxy M87, Messier 87. Okay, it's about 1 million light years away from us. So 1 light year is the amount of time, the amount of distance light will travel in 1 year. Okay, that's 1 trillion kilometers. Okay, so around 1 trillion kilometers, and this guy is 55 million trillion kilometers away from us. Huge distance away from us. Okay. Absolutely crazy distance. How can you see this guy if it's that far away? Because it's also very big. Okay. So the mass of M87, we know, is about a billion times the mass of our own sun. This thing here is called the solar mass, the mass of our sun, which is itself given here. Huge, huge numbers. These are very heavy objects, therefore called supermassive. They're extremely far away, okay. But we still manage to see them. Okay, so I'll try to tell you why we're able to see them and so on. And then I'm just setting the stage for the fact that these objects are absolutely astounding. The scales are phenomenal. This is a feat of astronomy. This is the best ever we could do. That's why it's taken so long. Okay. So what we should just before I go ahead, let me just tell you that for black holes, I'm not going to sort of discuss Einstein's theory. Einstein's theory of generality in any great detail. So I'm going to drop some facts here and there, okay? You're going to have to take them. If you have any doubts, if you think they're suspicious, you will stop me. Okay, so what we know from Einstein's theory is that if you take a black hole, which is more massive, it's going to be bigger. Okay? So it scales, the size of the black hole scales with the mass of the black hole. Okay? In particular, if you take the event horizon radius, all of you know what an event horizon is? It's the last surface beyond which you can't see, you can't escape from the black hole. So the radius of the event horizon is given in terms of the mass of the black hole in this form, by this way. Okay? C is the speed of light, and Gn is the Newton's gravitational constant. Okay? So this radius you can compute for M87 star from this mass. Okay? And what you'll find is that it's about 10 to the 10 kilometers. Okay? 10 billion kilometers, equivalent to 1.5 light years. So this black hole is so big, to get from one end of the horizon to another end, it takes light 1.5 years. Okay? So huge objects. Now, because they're huge, so huge, even though they're so far away, they make sufficiently large angles on our sky for us to actually be able to see them. That's the idea. Okay? So how we will compute? So let's say this is the black hole. Okay, it's at some distance from us. We're here. This is the distance. This is the size of the black hole. So this is this RH thing that I just told you about. So you can estimate what is the angle that will subtend on the sky. Okay. Because this RH is such a small number relative to D. This is 10 to the 10, and that's 10 to the 12 times 6, 10 to the 18. Okay. So it's a very small number. This is a very small number compared to this. So the angle, this angle, is approximately RH by D itself. Okay. If we compute this, it will turn out to be 20 micro arc second. Okay. What this means is the following. So micro is just 10 to the minus 6. What is this arc second? Typically we measure angles in radian or degrees, etc. An arc second is 1/60th of an arc minute. An arc minute is 1/60th of a degree. So the angle we are saying that this black hole subtends in the sky is 20 times 10 to the minus 6 times 1 by 60 times 1 by 60. So it's like 2 into 10 to the minus 10 or so degrees. That is the angle it's subtending on the sky. Okay? So very, very small angle. It is equivalent to if you placed an orange on the moon and you're looking at it from the earth, it would subtend the same angle on the sky. So when we say we're able to make an image of a black hole, we're able to resolve that small an angle on the sky with that telescopes. That's what we're doing. Okay. This thing here is the angular resolution, it's called, of the telescope. It's saying if there are features smaller than this, my telescope will just see it as a blob. Okay. It'll just spread. Let's say there's a point source, the telescope will just spread it into this whole circle. It will not be able to resolve finer features. So you look at this. This is roughly the size of this whole ring. Okay. There's something finer, like there's a finer feature, but we're not able to see it because the telescope is blurring to this angular resolution. Okay. This angular resolution is roughly 20 microns. Okay. So with our telescopes, we have now been able to actually reach 20 micro-arc-second resolution and therefore construct such an image. This has happened with data in 2017. And the paper, the data analysis, everything was finished by around 2019. So in 2019, this image was published. This is the first ever image of a black hole. So what you're seeing is that the black hole size is 20 microarcseconds, the horizon, and you have constructed a telescope on Earth. I'll tell you a bit about what this telescope does, which is able to resolve 20 microarcsecond resolution. This is the highest angular resolution instrument built by man. You can imagine, right? We're resolving 10 to the minus 10 degrees. It's extremely fine value. Okay, so I said radio light. All this light that we see is in radio frequencies. In particular, it is at 230 gigahertz frequency. Remember that your radio, FM radio, etc., it operates in megahertz. So 10 to the 6 hertz. This is in gigahertz. It's still radio. Okay, this is the same kind of wave. So this is 230 gigahertz radio wave that is emitted by some matter around the black hole. So that matter is emitting light, radio light. The radio light is reaching us. We're imaging it and forming this picture. Okay. Once we form this picture, we see that there is this central intensity depression. This intensity, you're collecting the total amount of intensity you're getting each pixel on the sky, and you can see this central intensity depression, which is a telltale smoking gun signature of a black hole. Why? If you imagine looking at the sun, okay, as you move towards, as you go, let's say, okay, so there's the sun. Let me draw a picture. So I'm looking at the sky and this is the sun, okay? Now I'm asking what is the total intensity here. I just look at the sky, the sun is here, I'm looking off away from the sun, somewhere in the sky. There's some intensity, fine. Now I start moving towards the center of the sun. As I come here, I'll see that the intensity is starting to grow. We are getting more and more light from the sun because the sun is a bunch of burning gas that gas emitting photons. I'm getting some intensity. So let me draw here intensity as a function of impact parameter. Okay. Impact parameter is just the radius of the sky. It's a fancy word for it. So let's say this guy is the edge. Okay. Let's say some zero light. Maybe there's some background light, whatever. And then it starts growing a little bit. And then as you come closer and closer, you would think it reaches a maximum value and then does this again, right? Why? Because as you look more and more in the line of sight towards the center, you are looking through a larger volume of the sun itself. So along the line of sight, there is more material of the sun that's emitting light. Does it make sense? What I'm saying? So you have one fluid element here that's emitting some number of photons, one fluid element here, one fluid element here. All of these are adding one photon, etc. And you add all these photons up and you get some intensity. But if you're looking, let's say, in this direction, there's a smaller path length, and therefore you don't get as many photons. Also, there's photons from this side. So basically, when you look at the sun, the intensity smoothly grows towards the center, and then it decays away from the center. This is not the case here. I see the sun, but this is true for any star. The star is sun, not a special star. All stars will behave in the same way. Okay. So the intensity will go towards the center. But here you see something completely different. You see, as you go towards the center, it actually drops. Now, what is an object that is trapping light? It's a black hole. So that's the sort of first telltale signature of the fact that this is a black hole. So, but we'll make some more cases. We'll get a bit more precise why this is a black hole. Okay. So, I also sort of, just to give you a sense of comparison, these guys are extremely massive. Look at M87. This guy's mass is 10 to the 9 times 10 to the 30, so 10 to the 39 kgs. The Earth is 10 to the 24 kgs, so it's like 13 orders of magnitude much larger. A billion, trillion Earths can sort of fit together to form this black hole. Okay? Trillion times the mass of the Earth. Not just that, just look at its size. This guy, let's say if it were a black hole, we'll argue it is a black hole. Its size is 10 to the 10 kilometers. So the entire radius on the sky, there's an angle, but if you were to think of it in linear size, it's 10 to the 10 it's a 10 trillion kilometers across, 10 billion kilometers across. If you took the Earth and packed all of it into this size, 10 millimeters, it would form a black hole. Okay. So for the Earth to form a black hole, its Schwarzschild radius is 10 millimeters.
How will we get these distances?
Yeah, so good, sorry. So this formula is what I'm using every single time. So what I'm saying is, let's say I know the mass of the Earth, you can measure that.
I'm not saying that. I'm saying how will you get the distance of the radius of what the mass of the black hole? How will you get that?
Yes, that's the next step. In a couple of slides, I'll just introduce how we get this, okay? Yeah, that's a good question. Okay, so, but before we go there, let me just make this other point. I just want to tell you that these black holes are also extremely compact. Okay? So, if the Earth has some radius, right, is 6,400 kilometers something in radius. Here, what I'm trying to motivate is, if I were to make the Earth a black hole, how much would I have to compress it? Okay. So I would compress the Earth to this size, millimeter size. If I do that, maybe it's 1 kilometer, right? Maybe this number is wrong. But if I compress it to such a small scale, 1 kilometer, in fact the entire Earth in 1 kilometer or whatever, 10 millimeter, this number is correct, then I would get a black hole. That's how compact these black holes are. That's how dense the matter is. So these are the most compact objects known to us. Okay. So these are very fascinating objects. Now another guy I want to tell you about. Okay, this image is wrong. Okay, so let me just shift to this figure. So we've actually imaged 2 black holes so far. We imaged M87 that we talked about. Okay, and we imaged Sagittarius A star. Sagittarius A star is this black hole over here. This is the black hole at the center of our own Milky Way. It's 1,000 times lighter, whereas this guy is 1 billion times the mass of our own sun. Okay, this guy is 1 million times the mass of our sun. This guy is some whatever distance away, 1 million light years away. This time, this guy is 26,000 light years away, just within our galaxy, the center of our galaxy. So this guy is 10,000 times smaller and 1,000 times closer. So its angle of the sky is going to be roughly the same size as this guy. Okay, and the EHT is able to resolve these two because the angles, these are the angles that we can actually resolve. Like I said, we built an instrument that can resolve these angles. So we can resolve this guy as well as this because they are roughly the same size on the sky, same angular size on the sky. What this figure is showing you is actually the linear size of these objects I told you the horizon is huge, etc., etc. So this is the sun's diameter. This is Sagittarius A star, the smaller guy, the one in our galaxy. This is the entire sun's diameter to scale with the image. This is Mercury's orbit. So the black hole at the center of our galaxy is the size of Mercury's orbit. The event horizon is the size of Mercury's orbit. It's huge. Okay. On the other hand, let's look at M87, the one that I talked about so far. The one that's in the faraway galaxy. This is Pluto's orbit. Okay. And Voyager, which is the farthest man has gone. Okay. There's a satellite that's been sent into space, it's been traveling for years, decades, sorry. So this is the farthest it's gone. So we have been able to explore the distance of the size of the horizon of the galaxy. Huge, absolutely huge objects. Okay. So these are supermassive objects. These are huge objects. They may be far away, but they're big enough that we can see them from here. The angles of this object in the sky are just enough that we can actually see them on here. Okay. So that's the story about these two objects, these two black holes. And now you asked about the mass. Okay. So Sagittarius A star, the supermassive at the center of our galaxy. This is how it was discovered. So this was a Nobel Prize that was given to a couple of people, Andrea Ghez and Reinhard Genzel, a couple of years ago. So what you're seeing here is measurements taken over 20 years in optical frequency, okay, by telescopes at University of California, Los Angeles. And these are all stars, okay, that they have tracked on the sky. Each of them is an individual star. You're seeing this in optical frequency, okay, just normal light. And what you see, look at this orbit. This guy, over 20 years, by the way, this is the year. So you see, look at the star. It comes close to this point. You don't see anything here, okay? It comes close to that point and it just slingshots around. All of these guys are executing orbits around some completely invisible point. There's nothing here in optical frequencies at all. Okay? So if you try to use, say, just Kepler's laws, okay, you know that if you have an ellipse, if you know what the orbit is, you can figure out what the mass is by Newton's law, and you know where the focus is, right? So I can tell you what is the mass at which focus. I'm able to tell you this with just this orbit, the yellow one. Look at that; it's perfect ellipse, right? Then I can take another guy. I can say, okay, that guy is also giving me the same ellipse. All of the guys are giving me the same ellipse. So I know the mass of the black hole, and I know the location of the black hole. It has to be a black hole. It's not emitting anything. And also, this guy is 1,000,000 times the mass of our sun. Okay? 1,000,000 times. So it has to be also small. It's also very compact. You know, it's quite localized center focus. So these kinds of things tell us that it's a black hole. So the argument is the following, right? It can't be million solar masses spread over this entire region. This million solar masses has to be roughly at the focus, right? For Newton's laws to create this kind of ellipse. So if it is that localized, if it is million solar masses and that localized in space, it has to be a black hole. Okay. These are some of the first evidences for the fact that this is a black hole. Now let me just sort of push the story home. So just look at this, okay? This is a different instrument. By the way, this is by this instrument called Keck. There's a couple of radio telescopes in Los Angeles. There's a different set of radio telescopes in Chile, okay, by the Gravity Collaboration. So two different teams constructed the same data and got the same answers, okay? Look at this. This star is the same as this yellow star, okay? It's a very famous star called S2. And look at this orbit. The points here are data points. So you look at the sky one night, you look at the sky, you look at the star another night, etc. And you track its location, and you fit an ellipse through this set of points. Look at that ellipse. It's a perfect ellipse, and the focus is right here. That's where the black hole is. Okay. That's the match between theory and observations. The data points are observations. The theory is this curve. Okay. Perfect match. Now look at this. These are two different stars. Again, another perfect ellipse, another perfect ellipse. The black hole is somewhere. Okay. You can see this is an artist's impression, but this is roughly what is happening. This is the star again. The closest distance is about just 120 times the distance between Earth and Sun. That's how close this star is getting to the black hole. Just 100 times the distance between Earth and Sun. And at this point, it's moving at relativistic speeds. The entire star, huge thing, is moving at the speed of light, half the speed of light. Okay, that's how extreme gravity is close to the black hole, and that's what you're seeing in all these images. I mean, you can see this, right? This is our entire star. Look at this guy. It's just slingshotting like that. Can you imagine a change in velocity of a huge star? That's how strong the gravity around this black hole is. Okay, so these are the kinds of early inputs that we had, which helped us measure the mass of this this compact object, this dark object, and this is how we knew. Okay, there's probably a black hole in that direction. Let's look at let's look in that direction in radio length, and then let's see what we get. Okay, so here I just put in some numbers. So the mass of Sagittarius A star from these measurements, okay, from this group and that group, matches very, very well. So it's around 4 billion times the mass of our sun, okay, from the 2 different groups. And the distance is, like I said, 26,000 light years. Here it's in meters. And I'm just dividing, like I said, the angles. Okay, I'm just trying to construct the angle and showing that it's actually 20 microns. So from these kinds of observations, from these stellar dynamics observations, we knew that there's a black hole. Its horizon is of the size 20 microseconds. So if we want to image this black hole, we need to build a telescope that is able to resolve these tiny angles. Okay? That's what we knew in the early 2000s, and that's when they started constructing this set of telescopes, okay? which we'll talk about. Okay, so how do we measure things as relativists? We use units that are called geometrized units, in which we set the speed of light and Newton's constant to 1. You've seen all these pesky G's and C's, we don't actually write with them. So I'm just letting you know that this is how we do things. So if you see a stray unit, you know what it means. So the speed of light is meters per second, something meters per second. So when you set C equal to 1, what you're actually doing is you're relating meters and seconds. Okay? Similarly, when you set G equal to 1, you're relating kgs and meters. You've already gotten rid of seconds in terms of meters, so now you're relating kgs and meters. Okay? So everything is in units of mass. Okay? Because you eliminated seconds from this, you eliminated meters from this, so everything is in kgs, or everything is in mass. So that's how we measure things in Einstein's theory. Okay? So in particular, distances, you will be able to show that this whole thing is actually meters. Okay? This combination is meters. This combination is seconds. You can show these kinds of things. Okay? So typically what we do is that we don't show the G and C. We'll just say 10m is the distance. Okay? 10m is the time scale. So these are the kinds of things that we do. Okay. So like we already saw, another thing that we do in astronomy or astrophysics is that when we are trying to measure the mass of a black hole, this black hole, that black hole, we don't measure it in kgs. What is 10 to the 30 kgs? That's a crazy number, right? The natural object is stars. We look at stars. We say, okay, is this black hole bigger than a star? Is it smaller than a star? Is this white dwarf bigger than a star? Smaller than a star? Okay, that's the kind. The stars are the usual like weighing scale, the units. Okay, and the star that we know best is our own star, the sun. Okay? So we measure everything in terms of the mass of the sun. Mass is anything. So solar mass, it has this nice symbol m sun. Okay? You read it as m sun. And one solar mass is 10 to the 30 kg. I showed this earlier. So now I am asking, what is the characteristic gravitational distance for the sun? Okay. So I am putting in m here and evaluating what that is. So that's 1.5 kilometers. Okay. You remember a few slides earlier, I said that 2 GnM over c squared is the radius of the horizon. What that means is, if you took the entire sun, all this 10 to the 30 kgs, and packed it inside 3 kilometers, it would also become a planet. Okay? That's what it means to say the gravitational distance associated with this mass. Okay? Good. So that the gravitational time scale is some microseconds. So what this means is, if you have, what you would imagine is, if you had, so let's say you had actually a black hole whose mass was equal to the mass of the sun. There's hypothetical black hole, and now you have some guy that is going around the circle, like on a Keplerian orbit. What is the orbital velocity of this guy? The orbital velocity of this guy, orbital speed, orbital time will be around 10 to the minus 6 seconds. That's what this time scale is. So this is what we mean by the gravitational time scales associated with the sun, and these are the kinds of ways in which we measure things in astronomy. Okay. Any questions at this point? Sure. What about you guys? Everything crystal clear? Okay. All right. Regular astrophysicist, sir. Okay. All right. So okay, black holes. All of us have heard about. Sorry. Okay. So all of us have heard about black holes. You've seen these funky cartoons. Black holes are causal edges of space-time. Okay? They are boundaries in our space-time because we can't actually see what is inside. Okay? So they are actually physical boundaries. You cannot see what is inside, and we call them causal edges. You cannot see what is happening behind the thing, so things could evolve in some other way inside, and you would not know. And in Einstein's theory, they are supposed to be very, very simple objects. There's something called the no-hair theorem, which means that black holes are defined by just two numbers. All black holes everywhere in the universe, their entire space-time is described just by two numbers. The mass of the black hole and the angular momentum of the black hole. Okay, how it's spinning. What is the amount of spin it has. That is it. Why? Because there's something called the Kerr solution. Kerr was a guy in the 60s. He found a solution to Einstein's equations. Einstein's equations describe general relativity. They tell you how space is curved, etc., etc. So he found the solution that describes black holes. The details are not important, but the solution depends on only two numbers: the mass of the black hole and the spin of the black hole. So that is why we think that all black holes in the universe are just described by these two things. Very, very simple objects. Just to sort of understand how fast, how absolutely crazy that is. Think about the Earth, right? To describe the Earth, you can't just use two numbers. You need the mass, you need the angular momentum, you need the magnetic field that we know. You need what is the height of Mount Everest. You need to know what is the depth of Mariana Trench. To describe the entire Earth, you need the density of the crust, the mantle, the core, whatever. You need so many different numbers. There's no way you just need two numbers. What we're saying is that these black holes, every black hole out there in the universe, you can just describe it in two numbers.
Yeah. So can we understand the charge of if it has some charge by these two parameters?
No. So fair enough. So typically,
I mean, it's a different solution. Yes, sir.
Yeah.
It's not a Kerr solution.
Yeah. So you can have charged black holes as well.
Yeah.
They're described by what's called the Kerr-Newman solution. It's a different solution. So it will not be within just this Kerr solution. It's an extension of the solution.
Yeah. So they can have more.
Yeah, they can have more parameters, but there's good reason to sort of think that astrophysical black holes do not have any charge. Okay? The reason is actually not very hard to imagine. So let's say you have black hole, okay, and you have let's actually think of it. So for Kerr-Newman, this solution, you have mass, spin, and charge. Okay. Let's do something simple. Let's say spin is 0, mass and charge. Okay. So you have a spherically symmetric black hole. It has a mass at the center and a charge, electric monopole, let's say, at the center. Now, if it's a spherically symmetric configuration with an electric monopole, you'll have some radial electric field. Okay? Now, here, just outside the horizon, in some small volume, what you can ask is what is the electric field strength? What is the electric field at this location? Huh? Sorry? Yeah, so the idea is that basically what you can show is that the electric field here is so strong that it will induce vacuum breakdown. Just like it happens during lightning, you will have a breakdown. And so you can create charges instantly over there because there's strong electric fields. And basically the opposite sign charges will flow down the black hole and neutralize this charge. So they'll cancel this charge. And the same charge guys will flow off to infinity. So there's some mechanism which may be a bit it's a bit hand-wavy, but
can you explain why it is so strong?
Yeah, because so the electric field scales with Q, right? Q by R squared kind of thing. So it scales with Q. The argument here is if Q is roughly of the order of m, the mass of the black hole, then it is too strong. You can show that the electric field is way too strong at the length scale of the horizon. So this statement basically means that there can be a Q, but it has to be very small compared to M. So essentially we say that astrophysical black holes are not charged. So that's why I make the statement that the mass and spin are what we use to define black holes.
Because if they are charged, they just start attracting and attracting.
It does do that as well. But like so this discharge, this vacuum discharge happens on very very short time scales. So let's say you somehow created a black hole with charge, okay, hypothetically. Then astrophysically what will happen is that it will just induce this breakdown of the vacuum outside the horizon, let's say. It can happen even inside the horizon. And basically the black hole will get discharged on very very short time scales. So once that happens, there is no other, like even if you have stray charge matter nearby, it's not going to really do that because there's no charge here itself. I don't know if that answers your question. Or...
Okay, so they only exist on very time short.
Yeah, the charge is some very very tiny short.
What happens with the charge?
Yeah. Okay. So okay. So the idea is that let's say you have very very strong electric fields. There's some effect in with quantum theory. But what will happen is if you have very very strong magnetic electric fields or magnetic fields or whatever in a very very small length scales, you can actually create pairs, virtual pairs, and so on. So basically, you will create an electron and a positron, let's say. And now, let's say there's an electron has been created and a positron has been created. If this is a positive electric charge, the electron will just get attracted this way. The positron get forced out that way. So what is happening is negative charge is flowing into the black hole. The black hole is positively charged. So negative charge is flowing in, total electric charge is reduced. And this process happens over and over again, and it happens very quickly. So on very very short time scales.
So the black hole also gains mass.
It loses charge. It gains very little mass.
So we can have a maximal bound over the amount of charge possible inside the black hole.
So yes, there's a number which I think is yes. I don't remember the number off the top of my head, but this discussion is in I think this paper. So these guys have a discussion, I think, in section 2 or section 3, I think, where they set a constraint on the maximum charge you can have on astrophysical.
Based on the vacuum discharge.
Yeah.
Not.
Yeah. Okay, any other questions from the side? From the back? Okay, alright. Okay, so here is a polar slice of a black hole. Okay? This is how a black hole looks like. Theoretically, when we describe black holes, this is what we draw. So you should imagine some spherical surface, right? That's this red surface. This is the event horizon, some sphere. Okay. So these black holes are these spinning black holes. They have mass and angular momentum as well. They have some interesting structures. So they have not just one event horizon, but they also have an inner horizon. They have two horizons. They come in pairs. Okay. So this dashed orange line, that's the inner horizon of the black hole. They have other interesting features. So at the center of the space-time, there's a ring. In the equatorial plane, there's a ring. This ring is actually singular. It's a space-time singularity. This is a feature of the solution. This is a problem that we hope Russell's theory of quantum gravity, or the grand unified theory, whatever you call it, string theory. These things will fix this issue. Okay? Now you should think of the space-time singularity in the following way. Let's forget about angular momentum. Okay? So let's say the black hole has no spin. Okay? So you have a spherically symmetric black hole. How is this formed? Imagine a spherically symmetric star. Okay? Now the usual story. You have in the star you have some outward thermal pressure because of fusion, etc., etc. And then once this fusion slows down, you start hitting iron, etc. Like after you fuse, the hydrogen gives you helium goes to lithium, etc., etc. And once you get iron fusion is endothermic. It does not release energy, so that is not preferred. So you don't actually generate outward energy through fusion. Fusion just stops at that. But what do you have? You have gravity always trying to attract you. Now you don't have an outward pressure, the usual story. So the star starts collapsing. It starts shrinking. And eventually there's only one thing that it can do, it can form a black hole. If the star is sufficiently massive. There's small masses, it will form a neutron star, but if it's sufficiently massive, it will form a black hole. Okay. Now what does this mean? So you have gravity acting. There's nothing stopping this contraction. So this mass is size, whatever, and x, it becomes x by 2, x by 4, etc., keeps going till it reaches zero size. So you have a situation where you have a finite amount of mass at one point. Okay? So the density there is actually infinity at that point. You have finite amount of mass divided by 0 volume, infinite. So that's a singularity. It's called a density singularity, and this causes also a space-time singularity. The gravitational field is singular at that location. Just like in electrostatics, what you have learned, at the center, like at R equal to 0, at the electric field evaluated at the electric charge itself is infinite. Same thing in relativity. Okay. This is the version when you have angular momentum. It's not a point; it's a ring. You can sort of imagine it because you had angular momentum to start with. So the angular momentum has to end up on some singularity which has some rotation. So instead of a point, you end up with a ring, essentially. Okay? So that's how you should think about it. So this is your ring singularity here. This is a density singularity, and it's a curvature singularity. So everything is blowing up over there. Gravity becomes very, very strong. This is a feature of the classical Einstein's theory. It's a problem. This is something that people are trying to fix. But there's a feature that you have in this solution that we use to describe black holes. Just so you know what is going on.
So what is the problem?
So you have this region here is actually a curvature singularity or a space-time singularity. And the fact that you have singularities is not a good thing in physics. So we try to, for example, regularize these things. So in the classical theory, whenever you have singularities, the quantum theory tends to fix these things. So for example, the electric charge, it gets fixed by something called vacuum polarization. The electric field gets fixed by what we call vacuum polarization effects, etc. We don't have a quantum gravity theory, so we don't know how this classical divergence is fixed in the quantum theory. But we expect that the full quantum gravity theory will be able to fix this.
What are the other than the outer event horizon, what are the other things?
Yes, good. I'm just getting good. Okay, so I told you about the event horizon, I told you about the inner horizon, I told you about the singularity, and like you said, there is also some other regions.
What about the inner event horizon? What exactly is this event horizon?
Yeah, so the way you should think about it is that outside here, right? Okay, maybe let me introduce this and then I'll talk about it. Okay, I don't know if you've heard this yet, but here the nature of time and space flips across a black hole. So space becomes time and time becomes space in some sense. Okay, that reversal happens again at the inner horizon. Okay. This is roughly one way to think about it. Yeah. Let me think about it and tell you. I don't know what exactly you would like to hear about the inner horizon. Maybe you can ask. Do you want to explain the question a bit more?
I think you're basically saying that normally, I know special ed, so you're saying instead of I in the time, it goes into I in the space coefficient.
Right.
And then it reverses back into I in the time coefficient.
Right. Yeah. That's one way to think about it. Yeah. So, yeah. Sorry, you have another question?
The reasoning you give for the black hole to not have a charge, why can't the same reasoning be applied to any massive body?
Any massive body. The idea is that, that's an excellent question. Typically in astrophysics, we don't have very much charge on most astrophysical bodies. That's actually just true, what you said. So, for example, if you look at the sun, it does not have an electric charge. Really. It has strong magnetic fields, but that's because there are currents inside, but there are no charges. There's some currents going around, but there's no free charges. So you generate magnetic fields. Electric field, bodies having electric fields is sort of rare, typically in astrophysics, on those length scales. Another way to think about it is that
The radius is
exactly. So these objects are also very compact. Black holes, like I said, they're very compact. And as you know, the electric field decays as 1 over r squared, right? So you should imagine the following. Let's say you have the same object. Let's say its mass is m. Okay, it's not a black hole. Let's say it's a star. Versus it's a black hole. Now you ask, what is the characteristic electric field at the radius for the same charge? This guy will be much smaller than the electric field here. It has the same mass and charge. So whatever this vacuum polarization effects are going to be much more stronger here as compared to here. So that's another sort of reason. But I want to stress that astrological objects typically, following your intuition, they don't actually have charge. Okay? They don't have electric charge. There will be currents here and there. There will be currents within it. There will be electromagnetic magnetic fields. Okay? So these things are quite common. Yes.
How would we measure if an astrological body has a charge? How do we know that?
That's a good question. So the way we usually measure magnetic fields is by looking at something called polarization. Magnetic fields and electric fields you can sort of gauge. So for magnetic fields, we do measure something called. Oh, maybe I'll just explain.
I guess you can measure the star.
The what? Sorry.
You can measure the star effect because of electric field in the spectrum.
Star gives us
line
the
sector.
Yeah, I'm just thinking whether it's feasible, whether you have enough line resolution. That I'm not sure. Okay, I'm not sure about this. Maybe we can talk later. I don't see. Yeah, sorry. Yeah, let's talk later. I don't think that's a good idea. Maybe that's a thing that you can do. I'm not aware.
What happened in A is greater than M?
Okay, good. Yeah, let me just make the last couple of comments. So there's this other interesting thing that I don't talk about, which is called the ergolism. Okay? This is a thing that happens only in spinning space-times. It's an absolutely fantastic effect. This is a purely general relativity. Okay? You do not see this in Newtonian theory at all. Now, what is the meaning? What is the ergolism? What is it? So now I said the black hole has the angular momentum. Whenever you have an object with angular momentum, it could be this, it could be the Earth, it could be the Sun, whatever. It doesn't have to be a black hole. Right? Once you have angular momentum, once you have mass currents, okay, in the electrodynamics theory, you have charge and charge currents, just normal currents. In Newtonian theory, Newtonian gravity, you can have masses, but we don't really care about currents, mass flowing in some light. That does not change the gravitational field. In Einstein's theory, it has a huge impact. It changes the gravitational field. So this is something that is completely new. It has no analog in Newtonian gravity, and this is called gravitomagnetism. Like in analogy with electromagnetism. Now, what does it do? It drags space-time. You've seen the usual picture of you have on your rubber sheet, and then you put a ball, and then the rubber sheet curves. I actually showed it some time ago on this slide. But if you have a spin, if the object is spinning, the rubber sheet also starts getting dragged. Okay. Maybe go to the rubber sheet. Yeah, you see, these curves, they will actually start twisting like this. Each of them will start twisting. So you can imagine like a whirlpool kind of thing. Okay. So the space itself is getting dragged. So this is called frame dragging or gravitomagnetism. And how we see this is if you place a spinning object, the spinning object will start to precess. This is an effect. Okay? I'm just telling, I'm not going to derive it or prove it for you, but this is one way you can check that this thing happens. If you just take a spinning object in Newtonian gravity and just put it there, it will not do anything. If it is spinning in one direction, what I mean is there is a top. Okay? The top spin axis is pointing in this direction. You take it and put it in a Newtonian gravitational field, and you work out the math. It's going to point in the same direction. Nothing changes. You take the same top, which is spinning in this direction initially, and you put it around the same object, but in Einstein's theory. Okay? The equations are slightly different. What you will see is that the spin vector will start precessing. Okay? This is some coupling between the spin of the top and the spin of the gravitating object. Okay? This is called frame drag. This is something that we measured on Earth. For example, the Earth is also spinning. Sorry, the Earth is also spinning. What we've done is we've sent satellites in the 2000s. There's an experiment called Gravity Probe P, and they put gyroscopes. Gyroscopes are spinning tops essentially, and they put it in some nice configuration, no friction with the whatever this, that, and the other thing. Put it on a satellite, launched it to very high altitudes, just above the Earth, and they measured this precession. And it's some very small effect, 10 to the minus 5 milli-arc second per year or something. Okay? It's a small effect, but we've seen. It's exactly consistent with Einstein's theory. So it's a completely new effect. Space is also being dragged. That's the idea. Now, just one thing I want to say. The ergo region is a completely interesting, it's a very interesting thing. If you're outside here, okay, just in the white region, sufficiently far away from the black hole, you can be here at rest in space. So in X, Y, Z, you can not move. You can, let's say, okay, you're here, the black hole is trying to attract you this way, but you can launch your rockets in the opposite way. You can thrust, you can generate thrust in this way and remain in the same location. X, Y, Z, you're at fixed X, Y, Z. So you'll just move in time. Okay? That's it. You're not doing anything else. But in this blue region, this is not possible. What is happening is, in this blue region, this ergo region, the black hole is dragging space so strongly that you cannot remain at rest in X, Y, in space. You have to co-rotate with the black hole. Okay? So that is a completely new effect that happens, and it leads to very, very interesting things. Okay? That I can, more than what I want to say here. For example, you can, I'll just say this, I'm not going to explain this a bit anymore. You can extract energy from the black hole from this region by doing some processes or continuous processes. So very, very fantastic like consequences of the fact that there's an ergo region in this space. Okay? So that's what I wanted to say about the ergo region. We'll talk about the like the A and M and all that in a second. But you have a question?
The precession is due to what? Like in the atom, it is due to both Larmor and Thomas precession. This
Yes.
is because of mass currents only, or is there a kinematic?
It is only mass currents. So kinematic in what sense? No. There's also a geodetic precession. There's also even if you don't have a mass current, you can have just the mass itself can give you. So let's say there are two scenarios. One, the central object is spinning, okay, and you just put one gyroscope, which has intrinsic angular momentum at one point in space. Okay? So there is a spin in the fluid, and this guy will start precessing. Okay? You are in the test body limit. This guy is not influencing this guy. Okay? Now there is another setting. This guy is not spinning at all. Okay? This guy, the compact object, is not spinning. It just has mass. And now on the outside, you don't have an intrinsic spin. You don't have a gyroscope, but you have a body moving on an orbital, on an orbit. Now you have orbital angular momentum. Okay? So now there is coupling between the orbital angular momentum and the mass, not the mass current of the central object. And this also precesses. There is something called geodetic precession or de Sitter precession. This is a different effect. It's not this kind of frame dragging, but it's also a frame dragging. So there are two different kinds of effects. In fact, when you see the precession of the perihelion of Mercury, it is this effect. So I don't know if you've heard about it. This is one of the classic tests that Mercury's orbit doesn't actually close. So it's not a perfect ellipse. If you look at the point of closest approach, or the furthest closest approach, perihelion or pericenter, that location actually precesses. Let me draw a picture.
So precession that you are talking about is the lens theory.
Yeah, so this one is lens theory. Okay, this is also what I just talked about is also lens theory, but it's different kinds of lens theory. So this is an orbital precession, whereas the earlier one I was talking about is just intrinsic spin precession. Okay, sorry, let me make it a bit clear. So here you have the sun, and you have Mercury's orbit. So it starts. Let's draw this axis. So it comes like this. So this is the point of closest approach. Goes away, and then this becomes the point of closest approach. Goes away. And then this becomes a point of closest approach. Goes away. Okay, it's a horrible drawing, but you get the idea, right? This thing starts precessing. Remember, in the Newtonian theory, you had this Laplace invariance vector, which fixed this immediate axis. You don't have this in here. This thing precesses, and this was one of the unexplained effects before Einstein. There's a very small amount. I don't remember the number. Very small amount per year or something. Yeah, 43 microarcs per year, right? Yeah. So very, very small number, but it was observed, like dating many centuries. And so this was something that Einstein's theory was able to explain perfectly. Just exactly. I mean, there's some other effects, but okay. So this effect is orbital lens theory, like we were just talking about. So the orbital angular momentum is precessing. You can think of it like that. Now you can have a different effect. Let's say this guy is spinning S1, and you have some other guy which is also spinning S2. What can happen here is that this guy there's a coupling between S1 and S2, like the spin-spin coupling that you've seen also in quantum mechanics. A similar kind of thing happens here. And now what happens is this guy starts spinning, starts precessing about its axis. So this spin also precesses. Okay. This is a slightly different thing than orbital length theory. It's also the same effect. It's just coming from train dragging, and this is a completely new effect that you get in the lens. Okay, all that to say that outside you can remain at rest relative to space. In this blue region, the black hole is just dragging space way too fast. You have to move with the black hole. So that's this new feature. Okay, so now another question that we had was, what is the difference between M and A? What's the time? Okay, all right. I'm gonna have to speed things up. Okay, so there's this mass and spin. We said are the two numbers that we use to describe black holes. So let's look at the zero spin limit. Okay, at zero spin, this guy is just zero. Okay, m minus m. This is zero. So non-spinning black holes don't have an inner horizon. They have a single horizon, the outer horizon. The outer horizon is at 2m. That's the formula I've been using all this way. 2gm over c squared. Okay. So that's what this is saying. And as the spin increases, the black hole size gets smaller. That's what you're seeing from here. Now the other limit. Okay. Also, in zero spin, what you can show is this yellow surface matches this red surface. There is no ergo region. The black hole is not spinning, so you don't have any frame dragging. You do not have this feature, this ergo region feature in non-spinning black holes. Now you can see there's the other limit, m equal to a. Okay. When m equal to a, what happens is that this horizon and this horizon merge. Now they merge. There's a single horizon, and this is what we call extremal black holes. Again, there is no inner horizon per se. There's just one horizon. The black hole is still spinning. You still have an ergo region. You have an ergo region, single horizon, and you have a singularity at the center. Now, what happens when you take a greater than m? This term is imaginary. This term is imaginary. So you don't have horizons anymore. You still have an ergo region, but you don't have horizons. Okay. On top of that, you still have a singularity. So you have a singularity which is not covered by horizons. This is called a naked singularity. So black holes, naked singularities, two different kinds of objects. Naked singularities are considered to be highly pathological because you have a singularity that's exposed to people everywhere in infinity. They are very pathological things, and we typically try to argue for why these should not exist. Okay? There are many maths papers that try to argue that from actual collapse of normal stars, these kinds of objects do not arise naturally. We can talk about this later if you're interested. Okay, so we've talked about all of this. Now that's the theory side. In astrophysics, black holes are not just merely hypothetical objects. They are real objects in astrophysics, and they're everywhere in the universe. Okay, they're not just one or two of them. They're like millions. Every galaxy at the center of every galaxy is a supermassive black hole. Within the galaxy, there are tons of black holes, tiny ones. Okay? We've seen them in all different kinds of ways. We see them because they have a huge impact on the nearby surroundings. So here's a cartoon impression. So you have black holes. They are stripping off gas from nearby orbiting stars. Okay? They are stripping off some plasma. They attract this plasma into disks, okay, accretion disks, pictured here, and they launch jets. So this is a jet. Yeah, extremely violent, extremely huge, extremely energetic phenomena, jets. What are they? So these are outflowing streams of highly magnetized plasma. Okay? So there are a lot of words. Essentially, what we're saying is that if you take a small volume element in this bright strip in the jet, what you will find is that there are some atoms, some gas, okay, which you can model as a fluid, perfect fluid, and then there are some electromagnetic fields that are carried by this plasma. Okay? So this is charged plasma. And in this region, the magnetic fields are much stronger than the fluid itself. The energy in the magnetic field is greater than the energy in the density of the fluid itself. Here are some details, might not be interesting, but these jets are launched by these black holes, okay, and they are visible far everywhere. Okay? For example, this is an image, this is an actual image now, of the jet in the galaxy Centaurus here. Okay. This is the entire galaxy, by the way. Okay. Somewhere in the center there is a black hole, and you're seeing these jets which are extragalactic, huge phenomena that are created by tiny black holes. Okay. By tiny I mean the black hole is still a million times the mass of our sun. The galaxy is huge, and this is even huger. The jet is even huger than the galaxy. Okay. So this is, by the way, this is a composite image with in radio light. Sorry, the orange stuff is radio light. Okay, taken by some observatory called Apex. In blue light is X-ray, and in true color you have this MPG as so the rest, the stars etc. in true color. So what you're seeing is, so this thing is the jet. Okay, you're seeing the jet in X-ray and also radio light. Huge jets. This is a jet in M87. The guy we talked about at the very start. That guy has a jet. Okay, what you're seeing, this is the black hole at the very center of the M87 galaxy, and this is the whole jet that it's launching. This thing, by the way, is 20,000 light years in size. The size of the jet is 20,000 light years. Hugely violent phenomenon. Okay, and this is the black hole that's powering this whole thing. What I sort of alluded to was, if you sort of try to ask what is it, how is the black hole powering this? It's actually using its spin energy and it's launching jets. There's some very beautiful physics there. So you see these kinds of jets. So you know that the black holes they're very active. They have lots of sort of imprints on observations, and of course we see the black hole images. These are the accretion disk itself. So I showed you in this artist impression that there's the accretion disk and there's this jet. These are observations, actual observations of jets in astronomy. This is how the accretion disks themselves look like. You have gas swirling around the black hole. The gas is extremely hot. Okay, the gas is hot, so it's going to emit some amount of light. This light is going to travel to us, and that's what we see. The images of the actual accretion disk around black holes. So the M87, the faraway guy, the Sagittarius A star, the guy in the center of our galaxy. Okay. So this we've seen anyway. So how do we sort of model these things? This is a numerical simulation done by one of my friends. So what you're seeing here is at the center you have a black hole, okay, and this is your plasma that is swirling around the black hole and is launching this jet. That's roughly what we're doing in the simulation. I'll explain how we do the simulation shortly, but this is an example of what a typical simulation looks like, numerical simulation on the computer. And they have very, sort of, as you can see, it's not a very simple environment. A lot of stuff is happening. Look, some colors are changing, etc. This is the change in the density and the magnetic field strength around these black holes. So one of the things that we are very interested in currently in the last decade or so and going forward is how can we make inferences about the black hole itself. If we want to ask, so we said from the theory side, black holes have to be these curved black holes, right? Einstein's theory is curved black holes. Now from observations, we ask, okay, we've seen this image of a black hole. Can we say, is this the black hole from general relativity? Was Einstein right? These kinds of things. So how do we answer these kinds of questions when you have these incredibly complex environments? So these are some of the things that we try to do. Maybe it's already an hour. I meant to only go till an hour. I think we've talked about black holes and stuff. Maybe shall I stop here and just take questions, or what do you think, organizers?
I think we can go ahead.
It's the end of the day also. I don't know.
Guys, do you have any problem with continuing?
Sure. Okay. Maybe I'll tell you one bit of theory and then we'll stop. Okay. Sorry. Any questions?
In the extremal horizon, extremal black hole,
Yes.
you said that the inner horizon is a place where the minus sign transfers from time to space, and other horizon is ulta.
Right.
So if they are the same horizon,
Yeah.
won't it basically be the same thing as nothing happening?
That's right. Exactly.
So if nothing is happening, then how can you even say there's a horizon there? If it's extremal black hole, what's the horizon?
So there's a bit more stuff there. We can talk about this at the end. Okay. At 5:30 when we're done, I'll answer. I'll not dodge you. Okay, I'll answer this question. It's a bit more. It's a bit longer, I think. It's a good intuition. We'll talk about it at the end. We'll come back. Okay, so let me just tell you how we're making these observations. Okay. So I told you what we're seeing, etc., etc. Let me tell you how we're doing it. So the EHT, first of all, is not just myself. It's a collaboration of currently I think 350 people. It's a global collaboration. It has people from everywhere around the world. Okay, China, Japan, Chile, everywhere. And yeah, this is one of our pictures from one of the collaboration meetings in 2021. Okay, so the collaboration has two marquee sources. It's M87 and Sagittarius Star, the ones that you see. These are the two marquee sources because they are big enough such that we can see. Okay, they're big enough in the sky and they are bright enough in the sky. There are other sources that are big enough, but they are not bright enough at the frequencies that we are observing these sources. So we cannot see. Okay. Does it make sense? So we are looking at the sky and we are only sensitive to radio frequencies. We are only sensitive to 230 gigahertz radio frequency. Now, if some other black hole is big enough for us to see it, but it's not emitting much at 230 gigahertz, we're not going to be able to see it. Okay. So these are two guys that are big enough and bright enough for us to be able to see them, and that's why these are the two guys that we've seen. And the broad aim, okay, with these black hole images is to perform experimental tests of gravity, to test Einstein's theory, to test the Kerr solution, okay, of Einstein's theory, etc. This is one kind of test. Another thing that we are interested in is how are jets launched. Okay, there is a theory for how jets are launched. We don't have observational proof that our theory is correct, and we are the only game in town because we can actually look at black holes all the way up close to their horizons. We're the only game in town that can try to answer this question, and this is something that we are currently doing. Okay. And this you can just forget about. Okay, so why do we observe in radio? So here is we're just looking at the Milky Way, okay, in multiple frequencies. What you can see is that there's a lot of stuff happening at various different frequencies. You can see that radio, you can see some bits in radio, but at, like for example, where's optical? Yeah, if you look at optical light, it's completely obscured by dust. Okay? There are other effects at other frequencies. So radio is the frequency in which you can actually look at the galactic center. That's one of the reasons. The other thing is that if you look at just on Earth, you have an atmosphere, right? So because of this, the kinds of things that you can observe from Earth, you can observe ultraviolet light, X-ray light, or gamma ray, because the ozone layer reflects or absorbs a lot of this. Okay? So you cannot observe at these frequencies. So what you can do is observe at optical or infrared frequencies or radio frequencies. And our black holes, the accretion disks around black holes, are not very bright at infrared and optical frequencies. So the only choice that we have left is radio frequencies. Okay. That's where these guys are bright enough, so we're going to observe at radio frequencies. This is something related, so you can see there are multiple different factors. One is what is happening in the galaxy itself. Another is what is happening in the atmosphere. And the last thing is the source even bright at these frequencies? So all these different factors tell us that we should look, radio frequency is the Goldilocks zone to look at these kinds of black holes, to make these black hole images. And that's what we do. And here is a computation again of the angular diameter of these black holes. So we said that this is the mass, this is the radius of the horizon, this is the distance, and this is the angular size of the black hole. Okay? 20 microseconds. So we know what we need to reach from the theory side. We know, okay, these black holes are 20 microsecond in size. We have to get to 20 microseconds. We have to do that resolution. We have a constraint on what observing frequency we can use, radio frequency. Okay, now we want to build a telescope. And what you know is that the angular resolution of your telescope goes in this way. The observing wavelength divided by the largest baseline. So it's, if you remember, this is the wavelength divided by the aperture of the lens. Okay? I forget what formula it's called. There's a 1.22 factor. What is this? Do you remember what this thing is?
Near and far.
Yeah.
Really?
Yeah, one of these things, right? The diffraction limit, I forget the name. Sorry?
Really far,
Rarefied?
Really?
Rayleigh. Okay, cool. Yeah, Rayleigh, I guess. Yeah, this is all like 20 years, 15 years ago for me, so I forgot the number. But anyway, so this is that formula, okay? This is the diffraction limited angular resolution of a telescope, okay? So now we know what this theta s has to be. It has to be 20 microarcsecond. If it is much bigger than that, you're not seeing the guide, you're not seeing the black hole, you're not resolving it. So you have a constraint on this. You have a constraint on lambda because you want to be in radio frequencies. Now you see, you want this number to be small. If this is smaller than 20 microsecond, you can see the source. Okay? So you want this to be small. So you want lambda to be as small as possible. Of the radio frequencies, you want the highest frequency radio, smallest radio. Okay? Is it making sense? So you want the smallest wavelength, highest frequency. That's why we choose high frequency radio, 230 gigahertz. Okay? It's very high frequency radio. If you go much higher, then doing the kind of technique that I'm going to describe is sort of nearly impossible. It's very hard to do this technique. Okay? In India, for example, we have megahertz astronomy, or like GMR, the giant meter wave radio telescope, which is there in GMRT, Pune. We have one of the best meter wave radio telescopes. These are the megahertz range. We cannot use this for the EHT measurements because we want very high frequency radio, because we want to increase the angular resolution. Okay? So you want the shortest wavelength or highest frequency. So we choose 230 gigahertz. It's very high. So we've minimized this factor. Now, what is the largest baseline that we can construct? Okay, it is the size of the Earth. So what we do is that we actually put telescopes at different points on the Earth and use interferometry to create a new virtual telescope, okay, which is the size of the Earth. So in Chile there is one telescope which is some size. In Spain there is a telescope some other size. Now these two together, they're measuring the same light, but you use them as an interferometer and think of and try to simulate a telescope which is the size of the Earth. Okay? I'll explain this in a second. But so this B is actually the size of the Earth. The Event Horizon Telescope is able to achieve this high angular resolution because the baseline that we're using is the actual diameter of the Earth itself. This is the biggest we can do. Okay? So this is the complicated part of our technology, and this is something I'm not an astronomer, I'm an astrophysicist, but this is something that our guys have been able to sort of really do. Okay? So looking to the future, actually before looking to the future. So what we're showing here is a plot between one of my colleagues, Dom. What he has drawn is the angular resolution on the x-axis and the amount of light you're getting at radio frequencies on the y-axis. Okay? And what he's drawing here is how many objects are there in the universe in different parts of this parameter space. Okay? So here we're asking how many objects are there that are very big in angular size, which means that the black holes themselves are very, very massive. So this is the angular size of the black hole. So either the black hole is very massive or it's very close to us. So how many such objects are there? There is one object at this, at this scale. That's the way to read this plot. And the y-axis tells you how many objects are brighter than this number. Okay. This thick line is the current Event Horizon Telescope's sensitivity, what kinds of objects, what kind of faint objects you can detect. Anything above this, you can detect the object. Anything below this, you cannot currently detect the object. And anything to the right of this, we can detect with the EHT because you have this angular resolution, this 20 microns. So we can detect all the objects that lie above this, and there's only one object, order one object. That is why you see Sagittarius, C-star, and X, just two objects. In the future, we hope to increase this, and we hope to decrease this, okay, decrease both of them, and then we'll start seeing more and more objects. In the next 5 to 10 years, we're going to go to space. Okay, so that means that your angular resolution is going to decrease because baseline is becoming larger. You're going to space now. We're also going to some slightly higher frequency, 1.5 times the frequency. So this factor is also decreasing a little bit. The wavelength decreases. So you are able to push down here. Okay, you're going to add more telescopes. So you're going to collect more and more light from the same object, and therefore you'll be sensitive to dimmer objects of the sky. So you're collecting more light from the same object. So this guy is also going to decrease. So we hope in the next 5 to 10 years to be able to detect 50 objects, 10 to 50 objects, okay? 10 to 50 black holes, new black holes. Okay, so I will skip this and this. Yeah, let me maybe just end on this. So here I'm showing you how the EHT actually works. This is a movie. On the left, I'm showing you where the telescopes are on Earth. This is for the first image of M87. And you're seeing there are 8 different sites, and you're seeing on the right the impact on the movie. Okay? This movie I think will loop a few times. So what are we seeing is the following. So when you see Yeah. Okay, when you see two guys, what you're actually sampling is the spatial Fourier frequencies of the image. Okay. Are you familiar with Fourier transforms? Fourier transform? Yes? Okay, fine. So you may have seen Fourier transforms in time. You can also do Fourier transforms in space. Okay. Instead of I omega t, you have I omega x. That's all. Okay. So this is an example of a spatial Fourier transform. So what you're sampling with an interferometer of this kind is spatial frequencies. Okay. What this means is the following. Let's say you have a long baseline. You can sample very fine frequency, very high frequency. Maybe this is confusing. Okay. I'll just say it for it. Just say it for it. It's an interferometer. Okay. Because it uses light appearing at two different sites, correlates this light, and does interferometry. And you can see that with increasing number of telescopes being added into this observation, the image gets sharper, better and better. So let's run this movie one more time and just see how many telescopes are looking at the source. Just 2 telescopes looks like nothing. Just 4 telescopes, it looks better. With a few more, 6 telescopes, 8 telescopes, already starting to look like the actual images that we see. So this is the technique that we use. We don't have the entire thing being the lens. Okay? So it's not completely perfect, but we take different points and use this technique called interferometry to actually build a Earth-size virtual telescope. Okay, so what we've learned so far, throughout this thing, is that we are looking at 2 black holes. We are able to look at 2 black holes because they're big enough and bright enough, and the frequencies that we can see them, radio frequencies, 230 gigahertz radio or 1.3 millimeter wavelength. We use this telescope called the Event Horizon Telescope, which is an interferometric array of 8 radio telescopes, which form a virtual telescope that is the size of the Earth. Okay? And you get an angular resolution of around 20 microns. So you're able to resolve these objects. And what you're actually seeing is black holes with their gas swirling around the black holes. The black holes are the gas is hot and therefore emitting a lot of photons. And what you're seeing in this bright orange is actually the photons coming from the gas around the black holes. Okay. So maybe I'll just stop there and take questions. And